So far, we have been talking about how E1 and E2 reactions are regioselective, which means there is preferential formation of one constitutional isomer. So let's take a look into the first example here. When 2-bromopentane is subjected to E2 elimination reaction, then it forms two different products. One is 2-pentene and the other one is 1-pentene. And between these two products, we can definitely tell that this is our Zaitsev product, and which is formed in major quantity, right? And similarly, if you consider this alkyl halide, this is a tertiary alkyl halide, and it can undergo E1 elimination reaction to give the following two compounds. And between these two, this is going to be the major product since this is the Zaitsev product. Now in this section, we'll see that E1 and E2 reactions are also stereoselective. We know that the E2 elimination reaction is a concerted reaction, which means bond breaking and as well as bond forming all happens at the same time. Now, in order for the E2 elimination reaction to happen, you want the bonds to the groups to be eliminated to be in parallel position. Say, for example, we want both of these bonds to be in parallel position, right? Only in that way, the p orbitals can overlap to form the alkene product. Now, there are two different ways in which the CH bond and the CX bond can be parallel to each other. One way is that they can be either on the same side of the molecule, like this, and such an arrangement is called a syn-periplanar arrangement. And the other way where both of these bonds are parallel to each other is where the two groups that needs to get eliminated are in anti-position. So here you can see that the two groups, hydrogen and X, are in opposite position. And this arrangement right here is called as anti-periplanar arrangement. If an elimination reaction removes both of these substituents from the same side of the molecule, then it is called as syn-elimination. And if they remove both of the substituents from the opposite side, then it is called as anti-elimination. So in E2, there is a possibility that you can get both of these eliminations, but anti-elimination is the one that is highly favored. Now let's see why anti-elimination is preferred. Let's look into the mechanism for the E2 elimination reaction in both syn-elimination and as well as anti-elimination. So here is our syn-elimination. So in the syn-elimination, the base is going to go grab this hydrogen and the departing electrons is going to form a double bond here and the X is going to leave. Whereas in the case of anti-elimination, this is going to be a backside attack where the hydrogen that is opposite to that of the leaving group is going to be abstracted, right? And these electrons are going to come in here and the X is going to leave. Now, between these two types of elimination, there are three important reasons that we can specify why anti-elimination is the favored one. Now, if you take a closer look into the two conformations, you can definitely see that the anti-elimination requires the molecule to be in staggered conformation, while the syn-elimination wants the molecule to be in eclipsed form. And we already know that the eclipsed form is unstable, while the staggered form is stable, right? So that is one reason why you want the elimination to be happening in the anti-fashion. The second reason is that in anti-elimination, the electrons from the departing hydrogen move to the backside of the carbon, which is bonded to the X, right? Whereas in the case of syn-elimination, these electrons are going to go to the front side of the carbon from which the halogen is going to leave. Now, we have seen that displacement reactions occur through backside attack. Okay, only in the backside attack we will have good overlapping of the interacting orbitals. And this is another reason why the anti-elimination is preferred. Now, the third important reason here is the electron-rich base is going to come in a direction that's opposite to that of the leaving group in an anti-elimination reaction. By doing so, there is going to be minimized electron repulsion between the electron-rich base, and as well as the leaving group. Remember, when the leaving group leaves, it's going to take its electrons and leave, right? So there will be, when the base is going to come in a direction that's opposite to the leaving group, there is going to be minimized electron repulsion. Whereas in the case of syn-elimination, you can see that the base that needs to go and abstract this hydrogen and the X, they are pretty much in the same position, right? Same direction. and therefore there is increased electron repulsion between them, making the syn elimination hard. So here are the three reasons why anti-elimination is preferred in an E2 elimination reaction. So because of all of these factors that favor anti-elimination, an E2 elimination reaction is stereoselective. In other words, there is preferential formation of one stereoisomer than another. For example, when you do E2 elimination of 2-bromopentene, you will get 2-pentene as a major product, regioselect because it's a regioselective reaction. But again, this 2-pentene is going to exist as two different stereoisomers, where some of it is going to exist as a trans isomer and some of it is going to exist as a cis isomers. Between these two, which one is formed in major quantity? It's obviously going to be the trans isomer, where the two groups are away from each other. So this is our major product and this one is a minor product. So we can now make a generalized statement about the stereoselectivity of E2 reaction, that if the reactant has two hydrogens bonded to the carbon from which a hydrogen needs to be removed, then both the E and as well as Z configuration product would be formed, because the reactant has two conformers in which the groups need to be eliminated or anti. So you can see that the hydrogen and Br, they are anti-position in both of these. Okay, and it results in the formation of both of these products, but out of these, trans is going to be the one that's formed more because it's the stable product. From the reaction coordinate, it is very clear that the trans product is obtained as the stable product because it goes through a lower transition state compared to the cis, right? And the trans is the one which is formed as the major product in this reaction, whereas cis is the minor product. So on the whole, a E2 elimination reaction is stereoselective, where one stereoisomer has been formed predominantly over the other. When there is only one hydrogen that is bonded to the beta carbon, then the major product that is obtained in an E2 elimination reaction is going to depend on the structure of the alkene. Let's take a look into this reaction. So here you can see that this compound, this alkyl halide, that needs to undergo elimination reaction, it has got only one beta hydrogen. So this is an alpha carbon and this is a beta carbon, and there is only one beta hydrogen on it. So this base comes and abstracts this hydrogen and thrusts these electrons to form the double bond, and the Br goes. So this is going to lead to the formation of E isomer because the two groups are in the two bulky groups are in the opposite direction. Here is one more example where you can see that Z isomer is formed. Here again, this is your alpha carbon, this is your beta carbon, and there is only one beta hydrogen, and this beta hydrogen will be abstracted by the base, and the electrons are going to come in to form the double bond. The Br is going to leave, but here in this case, it leads to the formation of Z isomer, where the two bulky groups are exactly in the same side of the molecule. Right? So in order to find the major product where there is only one beta hydrogen, then we have to look into the structure of the alkene that is formed. Okay, we cannot make any generalized statement that only E isomer is formed or Z isomer is formed. We have to look into the structure of the alkenes that are formed to find out the major product that is obtained. Just as we have seen in the case of E2 elimination reaction, the E1 reaction is also stereoselective, where it's going to lead to the formation of both the products E and as well as Z, and out of which the trans product is going to be obtained as a major product. Now let's consider this reaction. This is a tertiary alkyl halide, which under the presence of a weak base is going to go through the E1 mechanism. So we know that the E1 mechanism takes place in two steps. The first step is the formation of the carbocation, where the leaving group leaves. And here is the carbocation that is formed. Now, once the carbocation is formed, we know that the carbocation is a planar arrangement, right? So the electrons from the departing hydrogen can go and reach the positively charged carbon in either of the direction, leading to the formation of both of these products, E and as well as Z. Therefore, there is a possibility for both syn and as well as anti-elimination to occur. But the major product that will be obtained is the one where the two largest groups are on opposite sides of the molecule. So the two largest group here, the two ethyl groups are on opposite side, and therefore this is going to be the major product. And this one is the minor product where the two groups are in the same direction.